Okay, so in the next few videos, we're gonna kind of continue what we've been doing, where we've been looking at, say, functions and their derivatives and graphs. So just say I have some function that looks like this. Let's see, we'll go up, down, up, maybe just like that. And we'll have some function right there. Nice closed interval, nice continuous function. And when we look at it, our ultimate goal is for me to be able to give you some algebraic function f of x, and then you use your knowledge of calculus to get that graph. In order to do that, we're going to need a lot of tricks and a lot of theorems and things. And one thing I will point out as far as it goes, the next few sections are going to be us going through several theorems. They're really, really important. Like I remember doing them when I was in calculus. We had to present them. And so they are really important. But for the purposes of what we're doing, as much as you need to memorize the theorems, you also need to understand them. And we'll kind of look at that as we go through these. But first, in order to kind of lead into the theorems, suppose I have that graph. Well, what can I tell about that graph? Well, the first thing I have in math speak, okay, apparently this is going to dry out if I hold it up too long. Okay, in math speak, we have what's called extrema, or just extreme values. Maybe in more layman's terms, max values and min values. And if we look at the graph, clearly there's a maximum here, there's a minimum here, there's a maximum up here, there's a minimum here, maximum, minimum, and then at the endpoints we also have minimums and maximums. Essentially, put another way, kind of like mountaintops and valleys. That's a mountaintop, so it's a maximum. That's a valley, so it's a minimum, and vice versa. And now, using our knowledge of calculus, what could we say here? Well, one thing we've actually already kind of used is that if I drew the tangent line, the derivative right here, at that maximum, the slope of that tangent line is definitely 0. Which kind of leads me to believe, well, maybe, hey, look, there's a minimum and the tangent line has a slope of 0. There's a minimum, the slope of the tangent line is 0. So maybe maximums and minimums occur where the slopes of my tangent lines are 0. The problem is, well, clearly we said this is a minimum, but the slope of the tangent line is not 0. That is not straight up and down. I just had to make it look that way. It is slanted. It just looks straight up and down. And hey, right here, the derivative isn't even defined there. We said derivatives only occur where graphs are nice and smooth. Here, clearly, on one side, the slope of the tangent line is positive. On the other side, it's negative. And the two limits won't agree. So the derivative isn't even defined there. So apparently we can maybe say these maximums and minimums will occur where the derivative is 0, or the derivative has to be 0 for it to be a max or a min, or some form of that. And apparently there are also places where we can get max and mins where that isn't true. And so our ultimate goal is to be able to kind of come up with some theorems, some ideas that will actually allow me to say, oh, this is what the graph has to look like because of these rules. But before we get there, few definitions. First off, we can have what's called global extrema. Or if you will, global maximums and minimums. Then you can have local extrema, or local maxes and mins. I am not going to write out the formal definitions of these, but as far as it goes, the idea is pretty clear. On a graph, on an interval, say this is my interval A to B, you can have one global max and one global min. one value, we'll say. There could be multiple points that have the same value, but there's a global max, say a highest point, and a global min, a lowest point. Local extrema, local maxes and mins, you can have a whole bunch of those within an interval. If we look at this picture right here, if I was to say, where's the global max? Well, when I kind of look at this, I think about hiking because I like hiking. If that was a mountain range and I was hiking it, where's the global max? That's the highest point that I hike. Clearly for this graph, that's right here. So that would be my global max. Where's my global min? Clearly that's the lowest point that I hike, the lowest valley, which in this case would be right here. Local maxes, again, if you've ever gone hiking in the mountains, you kind of hop from mountaintop to mountaintop to mountaintop along a trail. Local maxes are just all the individual mountaintops you hike. So like we already said, there's a max right there, I get to the top of that mountain, then I go down, there's a max right there, there's another mini max right there, small little mountain. That one would be easy to hike, I'd like that. But we see we have multiple local maxes. They're all maximum on a little interval. And we have several local mins. There's one right there, there's one right there, there's one there, and one there. Ultimately, what we will want to do is find our local maxes, find our local mins, and then from those, find our global maxes and our global mins. Clearly, again, and I'm not going to write out all the formal definitions, but say, to be a global max, we'll say a global max that we'll call C. F of C has to be greater than or equal to f of x for all x in your domain, because it's a global max. So it has to be greater than or equal to every other value. And again, keep in mind, in theory, there could be multiple global maxes as long as they all achieve the exact same maximum value. Global min would be the same, except this would be less than or equal to. Local max and min would be the same. The local max, f of c would have to be greater than or equal to f of x, only instead of it being true on the whole domain, it would just be true on some interval around that max. So again, the definitions are pretty intuitive, but let's see. From this, we can get what's called the EVT, the extreme value theorem. We had the IVT, the intermediate value theorem. Now we have the EVT, the extreme value theorem. And to write it out, this is one of the theorems we want to write out formally. Let f be continuous on a closed interval AB, then there exists x1 and x2 in the closed interval AB such that f of x1 and f of x2 are global max and min. Values on AB. Or put another way, f of x1 is greater than or equal to f of x is greater than or equal to f of x2 for all x in AB. So, let f be continuous on a closed interval. If it's continuous on a closed interval, then there exists 2 points, x1 and x2, such that f of x1 and f of x2 are global max and global max and min values on the interval, and f of x1 is greater than or equal to f of x is greater than or equal to f of x2 for all x in the interval. And one thing I will just point out, This does not mean your max has to come first, like x1 comes before x2. It can be anywhere on the interval, but we just pick the highest value, and we call that f of x1. We pick the smallest value, we call that f of x2. This doesn't imply x1 is first and then x2 is second. But the proof of this, we don't really need to think about a lot. And generally speaking, the way this works when we're kind of working with theorems, one way to think about a theorem and think about why the theorem works is to try to figure out the conditions for the theorem and why you need those to make the theorem actually work out. Meaning, let's see, f is continuous on a closed interval, then this has to be true. So, if I have, let's see, a closed interval, that's A, and that's B. If I have a continuous function on that closed interval, do I have a global max? Well, yeah, I actually do right here. Do I have a global min? Yeah, I do right here. Okay, the theorem holds. That's pretty trivial. So, why is that important then? Suppose we have f of x. We'll let f of x be the function 1 over x. We know what the graph looks like just from 0 to infinity. Does that have a global max? Well, no, it doesn't. This goes up to infinity. But this is not defined at 0, so it's not defined on the interval 0 to infinity. It's defined on the open interval 0 to infinity. And it's the fact that it's open here that makes it not achieve the max, which is why this isn't working. So apparently, we need this thing to be on a closed interval, because if it's on an open interval, I can shoot off to infinity. Okay. Well, by the same token, if I just had, say, some rational function that looks like this, I don't care what it does to the left and the right, that's not continuous, and clearly it won't have a global max and a global min, because I shoot off to infinity and negative infinity, but it's also not continuous at that point right there. And again, we get this idea that in order for the theorem to work, the idea of continuity is important, and continuity on a closed interval is important. Continuity on the open interval allows for things to go to infinity. Once I have continuity on a closed interval, we'll make this one even more weird. It doesn't matter how messed up I make it. If it's continuous on a closed interval, then it starts somewhere, it ends somewhere, and it has to achieve all the values in between, which means somewhere there'll be a maximum value, and maybe to make it more clear, I'll make it dip lower. Somewhere there's a minimum value. There's my global min, there's my global max. This is my x sub 1 right down here. This is my x sub 2 right here. We're going to go through several more theorems. This is the first one, and I would point out, this doesn't mention derivatives and differentiability at all. This is actually an idea that comes from like pre-calculus. It doesn't require any of our calculus yet. That's kind of why we start here. But it does allow us to start getting an idea of graphs of functions and what they look like. Apparently, if I have a closed interval and a continuous function on that closed interval, then I have a global max and a global min. We're going to explore this a little bit more, and then we're going to expand on it and look at other theorems to kind of get a better picture of maybe where those global maxes and mins are and how I can actually find them algebraically.